Okay, so this is Unit 4, Organic Chemistry. It starts from, according to the specification, optical isomerism. For optical isomerism, isomer is when the molecular formula is same but the structure is different. It's known as isomerism, right? So in this, we are going to discuss optical isomerism, and the necessary condition for optical isomer is to have a chiral center. Let's say, uh, and hopefully you know this, isomer has two types, structural isomer and stereoisomer. This is the thing that we have discussed previously, and we are going to discuss optical isomerism. Okay, this one, and this one, and this one we already know. Chain means when the molecular formula is same but the chain is different. Position means when the molecular formula is same but the position of the functional group is different. Let's say propane 1 all, propane 2 all, butane 1 all, butane 2 all. So the molecular formula is same but the functional group is different. And then in this, you can see functional group isomerism means that when the molecular formula is same, but the functional group is totally different. Let's say if we have propanol and propanon. Propanol is an aldehyde, propanon is a ketone. Both have different functional groups, but the molecular formula is same. And what is optical isomerism? And in easy isomer, also known as geometrical isomer, also known as cis-trans isomer. Basically, in this, we have the two requirements. Number one, we must have a double bond between carbon-carbon, or then on the double bonded carbon, there should be different groups attached. Like let's say in this case, it can't give you cis-trans isomer. Why? Because the two hydrogens are same. Like the same groups are attached with the double bonded carbon, right? So let's say uh, for optical isomerism, what we do, chiral means it's a Greek word which means hand. What does it mean? We must have a chiral center for this. And if we have a chiral center, the four different groups attached with the single bonded carbon, carbon must have a single covalent bond. It doesn't have a double covalent bond. If you can see the double covalent bond between the carbon-carbon or anything else, so you are not supposed to just look at the chiral center. It's just wastage of time. So for the chiral center, we must have a single bond. Single bonded carbon, which is attached to four different groups, just like that. And if it has, so we can draw mirror images. Let's say if this is an image, and if I'm going to keep this molecule in front of mirror, so I would this one. So they are mirror images of each other. Okay, the left becomes right and the right becomes left. If this is just like that, so this would be just like that. It's 100% mirror images of each other. So means that they are optical isomer of each other. Okay. So let's say if he is going to ask in this way, he's going to give you the structural formula, not the displayed formula. So you must know where is the chiral center. If there is a chiral center, then you have to draw the mirror images of each other. So it has a chiral center, yes, it has a mirror images. So I would say that I would be drawing this one just like that. So the necessary condition is to have a chiral center. Okay. So, and then in the recent paper, and of course, this is in the syllabus, he would be giving you the molecule and you have to tell the chiral center, how much chiral center it has. It may have one, it may have two, it may have three, it may have six, it may have seven, depends on the compound given. Okay. So the thing is that we have to only look at the carbon which has different groups attached. Let's say if it has this one hydrogen, this is CH3, this is fluorine, and this is different. So I would say that this carbon is a chiral carbon. Okay. If I'm going to consider this carbon atom, so this is attached with different, 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 and different. So this would be a chiral center, of course, right? So, and then what is optical activity? What we do in this one. So whether the compound is optically active or not. So we have a procedure that is known as polarimetry. We do polarimetry just like calorimetry or a colorimetry, right? So let's say in colorimetry, if you remember when you do past paper related to kinetics, so ever they ask, we can determine the rate of reaction. So if we can see any colored compound or a colored substance or a colored molecule, so we can say colorimetry. We can observe color, how fast or how slow the color is going to change, so we can just determine the rate of reaction. And if there is a heat change, whether the reaction is exo or endo, so we can do calorimetry. Calorie means heat. And same goes with this one, it's a polarimetry. We measure the optical activity of the compound. Okay. If you have ever listened about glucose, which is just for the low blood pressure, if you have a low blood pressure, so you can use glucose. It's called D-glucose. D means what? Dextrorotatory. L means levorotatory. So, of course, both are optical isomers of each other. It's very interesting. D-glucose is not toxic. It's a human friendly. Uh, and when you would be taking L-glucose, it's a very toxic compound. What's the difference? Nothing. It's just like that. If this would be D-glucose, so this would be L. So arrangement matters. Okay, arrangement in space, that is called spatial arrangement, matters a lot. So the property totally changes, right? So what we do, we take monochromatic light and it's a polarizer. What the polarizer do? The monochromatic light is going to emit the light in all directions. So what the polarizer will do, it will filter the light in a one direction. Let's say the light is on y-axis only. The light is on y-axis only. If you have ever seen a laser light, it travels on the same axis. It's not like any other light which spreads all the way. No. So this polarizer will only allow the rays which are on the axis, and they will block the rays which are on the z-axis or on x-axis, right? So and then we have this polarizer which is on x-axis. Of course I can't see anything because all the lights are, it's just to make sure whether the light has polarized or not, like the rays has filtered off or not. So the rays has filtered off. It shows that when I can't see anything means that the rays are traveling on a y-axis, not on the x-axis. That's why I can't see anything. Okay, no light passes through this slit. So, polarimetry is to measure the amount of optical activity, just like that. Okay, so what we do, alpha is the angle of rotation that is to be measured. If alpha is positive, so means that the rotation is clockwise, and if alpha is negative, so the rotation is anti-clockwise, right? So, so this behavior will decide whether the compound is L or D, like dextrorotatory or a levorotatory, right? So, so we have to see this. And remember, for this all, we must have to check the presence of a chiral center. Is there a chiral center or not? If there is, so you can go for all. If there is no, so you are not supposed to go ahead. Okay. And what is racemic mixture? Equimolar mixture. Like if we have 50-50% of the two enantiomers that has no optical activity. Let me explain what are enantiomers, right? So first of all, what is D or L? Like what is dextrorotatory or levorotatory? Dextro means like you have put your sample in a polarimeter and I'm just looking to the sample through this one. It's just like a microscope. We have an eyepiece over there and this is the positive sign. Like this is the sign, so we can just take an idea whether the light is rotating or not, or we can also measure the angle that is called alpha, how much the light is rotated, or whether it is rotated clockwise or whether it is rotated anti-clockwise, right? So If the rotation is clockwise, then the substance is dextrorotatory, and if the rotation is anti-clockwise, then the substance is levorotatory. Okay. Uh, so, let's say I told you this, you can say they are optical isomers of each other. Why? Because they are mirror images of each other. Okay. So they are called enantiomers. They are called enantiomers, right? They are called if this mixture has a 50-50%, so overall there would be no optical activity. Let me explain why. If this compound is rotating the light clockwise, in the same way this compound will be rotating the light anti-clockwise, so overall there is no change. So I would say that uh, what is racemic mixture in which you have the same moles of the both enantiomers that has no optical activity. It's the same as, let's say, if I have a chair, okay, just like that, and let's say if this is you. Okay. And this is me, let's say. I'm applying the force of 5 Newton. You are also applying the force of 5 Newton in the same way, at the same time, at the same place, with the same strength. So the chair won't move. You know why? Because the forces are canceling each other, right? So why the light is not rotating? Why there is no optical activity? Because you have a two compounds, and interestingly, both have the same amounts, both have the same thing. So, of course, if one compound is rotating clockwise, another compound will be rotating anti-clockwise. So there is no, like in the end, I would say that the light is not rotating anymore. So so it has no optical activity, right? Uh, And then why do we do these things all? Like, why do we study polarimetry? Why do we study D or L or just like that, chiral center, each and everything? And why do we measure, like, what's the benefit? What's the advantage of these optical isomerism? First of all, I told you that the properties are totally different. If some compound is human friendly, so another would be very toxic. So we have a drug that is called anti-cancer drug cisplatin. I'm talking about I want to give you the importance of isomerism. Just we think that we have just only changed the position, just we have a mirror images. So what they would do, cis and trans. Cis is the anti-cancer drug, but trans is not. What's the difference? What we do, we just flip the uh, substances. If CH3 is upward, so let's say if this is hydrogen, in another compound, what I would do, I would just flip it. The property, like changes a lot. In the same way, if we have a D glucose or L glucose, or D optical isomer or L optical isomer, so the properties are totally different, right? So let me show you the mechanism. If you know about that SN1 and SN2 mechanism, SN1 means the tertiary carbocation, or I can say the tertiary halogenoalkane is going to give you this SN1 mechanism, right? Because in this mechanism, you can see the steric hindrance, which is caused by the bulky groups. This is CH3, 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 just like that. And this is a halogen. And let's say this OH cannot attack to this partial positive carbon. You know why? Because bulky groups are attached. There is no way that the OH can go to this partial positive carbon. It cannot come from the front because the halogen is attached. There would be a repulsion between the two negative species, right? It won't go from the back end side. You know why? Because there is a steric hindrance, because we have the bulky groups attached, that is called CH3. If you can just imagine the 3D diagram of this molecule, so you will see that like the balloons are attached. There is no way to go. So what it would do, first of all, this bond has to break down just like that. Chlorine has to be removed from this partial positive carbon. Now in the second step, the OH minus will easily attack on this positive center, on this positive carbon, and alcohol is formed. So this is substitution. OH has substituted this chloride. This is called nucleophilic substitution reaction in two steps. And this is tertiary halogenoalkane, so this is SN1 mechanism. And if you can see SN2 mechanism, this is primary halogenoalkane, right? Primary halogenoalkane means this reaction would be in one step. Because there is no steric hindrance, the coming nucleophile can easily attack on the positive carbon. So there is no need to do this reaction in two steps. Okay. Uh, so you can see that this OH minus can attack from the back end side because there is no steric hindrance because this is only CH3 and this is only one hydrogen. So the small groups are attached. Okay. There is an empty space. The coming nucleophile can easily attack. So what it would do, of course, the valency of carbon is 4. So carbon cannot make 4 bonds, cannot make more than 4 bonds, just like that. This is called transition state. It has a very high activation energy because we know that the valency of carbon is 4. So this is highly unstable because in this compound, the carbon has 5 bonds. What the dotted line shows, we want to show that this OH is going to make a new bond with this carbon, and this Br is going to be removed from this carbon. Okay, so one is coming, another one is leaving. So this is leaving group and this is coming group, right? So of course, it has to go because OH minus was coming to replace this halogen, so it has to go. It has gone just like that, and you can see that the OH is attached. Let me show you the major difference between SN1 and SN2 mechanism. In SN1, you can see the place of the nucleophiles are same. Like let's say if the chlorine is a nucleophile and OH is also a nucleophile, so the position is same. Chlorine was attached on the right hand side. The OH is attached on the right hand side. If you can see SN2 mechanism, if this was bromine, so this is OH. So the position is totally different. You can see the position is totally different. Like I can say the position is just flipped, isn't it? The position is just flipped. So so what it shows, if the position is flipped, if the position is not flipped, what it shows. So if the reactant is dextrorotatory, then the product would be levorotatory. What do you mean by this? Means that if this is the mirror image of this one, of course, this is, isn't it? So if it would be rotating the light anti-clockwise, right? Let's say it's levorotatory. So the product would be dextrorotatory. If you can see, if you are doing a polarimetry of the same compound of the reactant and the product, so I can take an idea about the mechanism, whether the reaction is SN1 or whether the reaction has SN2 mechanism, right? So in SN1, there is no, I would say that if the reactant is rotating the light dextro-rotatory like clockwise, so the product will be having the same behavior because I told you that the position of the nucleophile has not changed. I'm talking about SN1 mechanism. But in SN2 mechanism, the position of the functional group is totally changed. I'm talking about this one and this one, right? So that's why they are saying that if the reactant is dextrorotatory, so the product would be levorotatory. So after looking at this statement, I can say that the mechanism is SN2, not SN1. That's the importance of, according to your syllabus requirement, Unit 4 at Excel. So we must know this. Why do we do this? Why do we study optical isomerism? That's an importance of, like we can just determine whether the mechanism is SN1 or SN2, right? So, okay. And if the reactant is dextrorotatory or levorotatory, but the product has no optical activity, hence the mechanism is SN1 mechanism. Okay. So you will see this accordingly in the past paper. Uh, and then we have a carbonyl compounds. Carbonyl compound means the compound which has carbon double bond oxygen. Uh, So we have two types of carbonyl compounds. Remember, carboxylic acid and ester. They are not supposed to have a carbonyl compound. Carbonyl means it's a C double bond O. Left or right hand side, we must have carbon in ketone, and we have hydrogen in aldehyde. So ketone means both have like on the right and left hand side we have alkyl groups, R group. We may have one carbon, two carbon, three carbon, four, five, six, seven, eight, infinite. So suffix is on, of course. We have propanon, butanon, pentanon, hexanon. It's just like an alcohol. We do ethanol, propanol, butanol for alkene, ethene, propene. In the same way, we have the suffix for ketone is on. So we have few family members of a ketone. So we have to focus on the functional group. What the functional group is there, right? So we must know this one. If this is, so this would be a ketone, right? Whether it's a straight chain compound and whether it has a branched. It may have one branch, two, three, four, five, six, so on. This is the displayed formula of this compound, and this is the skeletal formula of this compound. This is going to be propanon. So you are supposed to know about how to write down the structural formula, how to draw the displayed formula, how to draw the skeletal formula, how to draw the molecular formula, how to draw the empirical formula, right? So you must know these things, otherwise you would not be able to decide the reagent and condition. If you remember when we were doing the past paper, examiner has given the questions in a different way. Sometime he would be giving you displayed, sometime he would be giving you skeletal, sometime he would be giving you structural. So if he has given a structural formula, like everything is messed up, like CH3, CH2, CH, CO, CH2, CH3. So first of all, we have to decide what the functional group is present. Let's say if we have mixed aldehyde and ketone. So after doing this, we can't decide whether the compound maybe oxidized or maybe reduced, which type of what type of oxidizing agent I'm supposed to take. Let's say whether it's an ester, whether it's a carboxylic acid. So you need to know how to convert the skeletal formula into the displayed formula or vice versa. And this is going to be aldehyde. So the suffix is al, methanol, ethanol, propanol. This is your, I'm not supposed to write, of course, hydrogen. This is just like that. So this is called ethanol. Then you have propanol, butanol, pentanol, hexanol. So this is an aldehyde, right? Or, yeah, if you can see the bonding, I'm talking about carbonyl, right? C double bond O. So the bonding, I can say that we have two double bonds. The one which is present between the carbon-carbon and the one which is present between the carbon and oxygen. So this bond is non-polar, but this is polar. Why? Because they have different elements. Oxygen is electronegative, highly electronegative, and this is lower electronegative. Due to the difference in electronegativity, oxygen would be having partial negative charge and carbon would be having a partial positive charge. So uh, so of course, this is more reactive. Okay, so if any nucleophile can easily attack on the partial positive center of carbon. But on the other hand, if you can see the carbon-carbon double bond, I can't say that this is going to be partial positive and this is going to be partial negative, because the both elements have the same electronegativity. So there is no difference in charge. So of course, I can say that this is going to be non-polar. Permanent dipole is present in carbonyl compounds due to the difference in charge, due to the difference in electronegativity, right? So this is going to be polar overall. But of course, it doesn't mean that it won't be having any London force. London force is present everywhere. Okay, London force is present everywhere, but you have to check whether the compound is polar or not. So we would see, of course, this is an aldehyde or a ketone, both have oxygen group. So of course, both are polar. So means that in short, I can say that in aldehyde or ketone, there are two types of forces that would be present in this. Number one is London force, which is also known as dispersion force, IDID force, temporary dipole, and another one is the permanent dipole, right? So then boiling point, what's the difference? Of course, CH4 has only London force. It's not polar, it's non-polar because It has no any highly electronegative element, or I can say there is no major difference between the electronegativity of the two elements. This is non-polar. So it doesn't have a permanent dipole. If you can see this one, this is an aldehyde. It has the two forces like London and the permanent dipole. It's more stronger than the London force. So the melting and boiling point of methanol would be higher than that of methane. Okay. In the same way, we have alcohol, we have carbonyl, we have alkane. So we can do a comparison between these three. If you can see alcohol, it has a London force. As I told you, it is present everywhere. And you have a permanent dipole and you have hydrogen bonding, of course, due to the presence of oxygen. Uh, and in a carbonyl compound, there are two types of forces. Number one is London. Number two is a permanent dipole. There is no hydrogen bonding, remember. There is no hydrogen bonding between the two carbonyl. Remember, between the two carbonyl, there is no hydrogen bonding. Yeah. Or in alkane, only the London forces are present. So I can rearrange it on the basis of the strength of the IMF. So the alcohol would be at the top because it has the strongest IMF, that is hydrogen bonding. And afterwards, if you have this carbonyl compound, it has a permanent dipole. Despite it doesn't have any hydrogen bonding, but permanent dipole is more stronger than the London force. So then it has a higher boiling point, and the lower one is an alkane because it has a very low, very weak attraction that is called the London force. So in this way, you can do a comparison. What if I have aldehyde or a ketone, right? So it says ketone has a slightly higher boiling point than aldehyde. You know why? Both are polar, both have a permanent dipole, both has a London force. So why the ketone has a higher boiling point? Uh, IMF depends on the two factors. Number one is the surface area. Number two is the number of atoms, or I can say the number of electrons. In a ketone, you can see uh, like the number of electrons, right? You can see the number of carbon increases, so the number of electron increases. When the number of electron increases, so means that the IMF would increase, remember. Okay, so let's say this one, it has a lower surface area, it has more branches, and it has a higher surface area. It has no branch, it's a straight chain structure. If it has a higher surface area, so the IMF would be higher. And if the IMF would be higher, so the boiling point would be higher. Okay. So we have to see the two factors, right? And afterwards, we need to know the solubility. So I can say that both are, have to see the, let's say, uh, the carbonyl compound which has less number of carbon atoms. Let's say the very simple carbonyl compound is methanol. So methanol, it's more polar as compared to the propanol. You know why? Propanol means it has two more carbon atoms in addition of the carbonyl group. So as the number of carbon increases, you can see as the number of carbon increases, so the non-polar part increases, isn't it? As the number of carbon increases, so the non-polar part increases. When the non-polar part increases, so I would say that the solubility will decrease. Like dissolves like. Water is polar. So water dissolves the polar substances, not the non-polar ones. So if in your compound there is a higher part of a non-polar part, so the compound would be having a lower solubility. And if you have a less number of carbon atoms, what does it mean? The less number of carbon means that if you have a less non-polar part, so the solubility of that particular compound would be higher in a polar solvent, and the polar solvent, of course, is water, right? Like we have another polar solvents as well, but I'm talking about water. Then, as I told you, between the two molecules of aldehyde or between the two molecules of ketone, there is no hydrogen bond left. But when this aldehyde, this carbonyl compound is dissolved in water, so it's gonna make hydrogen bond with water. This is the structure for water. It had hydrogen bond, but with water. But between two molecules of aldehyde, hydrogen bond is not present. Okay. Uh, okay. Then how can we distinguish between aldehyde and ketone? So it's very easy. We can have two tests. Number one is Fehling solution. Number two is Tollens reagent. Fehling solution is also known as Benedict solution. So, and both are oxidizing agents, mild oxidizing agent. If you're talking about Fehling solution, it's also an oxidizing agent. If you're talking about Tollens reagent, it's also known as oxidizing agent. But they are mild, they are weak, they're not as strong as KMNO4, K2Cr2O7, right? So the Fehling solution means what? It's a solution of copper plus 2. Of course, the color is blue. So when you are adding Fehling solution into the sample, if the sample will be containing aldehyde, so Fehling solution will be changing its color to give you the red precipitate. The red precipitate. Okay, solution can the red PPT. If you can see the red PPT, means that aldehyde is confirmed. If you can't see any red precipitate, so means that aldehyde is not confirmed. Aldehyde is not confirmed. It's a ketone. In a tolerance reagent, in a tolerance reagent, it would be giving you silver mirror if you have an aldehyde. But if you have a ketone, so it won't be giving you a silver mirror. No change. No change, right? So So as we know that aldehyde can be oxidized further, but ketone cannot be oxidized further. That's why they're not going to react with a ketone. It would not be giving you any positive observation with ketone. They both reagents would be giving you the positive observations with an aldehyde because aldehyde can be oxidized further and they are oxidizing agents, so they would be reacting with an aldehyde only or iodoform test. This test is used for the following. Number one is a methyl ketone. Number one is CH3CHOH. I can't say that it's a primary alcohol or it's a secondary alcohol. If you have CH3CHOH, CH3CHOH, so if you have CH3CHOH, so it would be giving you the positive test for iodoform. Let's say, like most of the people say that iodoform test is positive for a secondary alcohol. So what about ethanol? Ethanol is a primary alcohol. But ethanol can give you iodoform test. You know why? Because ethanol have this condition. So if any condition, so that compound would be giving you the positive test for iodoform. Like of course iodoform would be formed and the color for iodoform is yellow solid. It's CHI3. So it's a triiodomethane like CH3. Let's say I'm going to add iodine and OH. The reagents for iodoform test is I2 plus NaOH. So let's say if I have this one, it has a methyl ketone CH3 C double bond O. So I would see the yellow precipitate after adding iodine and OH minus. So means that CH3 C double bond O group is confirmed. Okay. And if you can see this one, it wouldn't be giving you the positive with iodine and NaOH, because it's ethyl ketone. It's not a methyl ketone. There is a difference, right? So the requirement is CH3C double bond O, not CH3C2C double bond O. Yeah, it would be giving you yes. And the rest of the part would be giving you. This is very important. Remember, this is very important. Yeah, most of the students know. Yeah, it would be giving you the positive result that is yellow precipitate. But what about another part? What about another part? So of course another part would be giving you this. It's not a carboxylic acid, it's the salt of carboxylic acid. Why? Because I have used sodium hydroxide. First of all, the carboxylic acid would be formed, but of course in the mixture, in the same beaker, in the same container, I have sodium hydroxide, so it would be reacting with the sodium hydroxide and it would be giving you the salt of that carboxylic acid, or I can write the sodium salt of that carboxylic acid because OH is coming from NaOH. Okay. Uh, iodoform, no. Iodoform, I have to draw the structure that is this. Yes, it has CH3CHOH. Yeah, it would be giving you the positive result. Yes, no, yes. So I told you the condition if any compound is having these two conditions, number one is methyl ketone, number two is CH3CHOH, so yes, it would give you the yellow precipitate. Then this is a very common topic. It's a very easy topic, oxidation of aldehyde. Aldehyde can be oxidized. Oxidation is a removal of hydrogen. Hopefully you know that. Oxidation is a removal of hydrogen, right? So aldehyde has a hydrogen, which is this one. It has to be removed. Like it can be removed, I can say. Why the ketone doesn't oxidize further? There is no hydrogen to remove. Oxidation is the loss of hydrogen. There is no hydrogen, so what am I supposed to do? So we can say that ketone is not going to oxidize further, but aldehyde does because aldehyde has an hydrogen. So what would be the product? Carboxylic acid. And what type of oxidizing agent I'm supposed to take? K2Cr2O7, but acidified. Acid is used as a catalyst. Acid is used as a catalyst. So it is ethanoic acid. If you are taking ethanol, so you would be having ethanoic acid, ethanol to ethanoic acid, propanol to propanoic acid, butanol to butanoic acid. So the design, the structure, the setting, the arrangement of the elements would not change, but only the aldehyde functional group will be changing into the carboxylic acid, and that's it. Okay. Observation is orange to green, right? This is heat under reflux. This is heat under reflux. Okay. And what if you have ketone? Of course, ketone cannot be oxidized. So there is no reaction. There is no observation. The color remains orange. Uh, can you tell me this? If I'm going to add K2Cr2O7, what you would observe? Yes. If I have this compound and I'm going to add K2Cr2O7, so what you would observe? Yes. Can you hear me? First of all, we have to first of all we have to identify what the compound is, what the functional group is present. This is an aldehyde, isn't it? This is an aldehyde. So aldehyde can be oxidized further. Yeah, if aldehyde can be oxidized further, so I would say that it can be oxidized into the carboxylic acid after adding K2Cr2O7. It's very easy. So let's say if this is a ketone, of course, ketone cannot be oxidized, but it can be reduced. You can see I'm reducing it in the presence of LiAlH4, that is lithium aluminium hydride, right? I can have secondary alcohol. You can see, isn't it? This is secondary alcohol, and this is a ketone. This is an aldehyde. So if you are going to reduce it, you would be getting primary alcohol. So you can make the summary notes. From the ketone, you can get secondary alcohol. From the aldehyde, you can get primary alcohol, right? After reducing it. And the reducing agent is LiLH4 in dry ether. Why you are taking dry ether? Because in this lithium is present that is going to be very reactive. It is present in group 1. That's why. You are not supposed to take water as a solvent. The ether is as a solvent. Uh, this is a summary chart. You can take an idea. This would be very helpful for you, right? You're supposed to write it down. Then we have nucleophile. What is nucleophile? Nucleophile means nucleus loving, can be negative, can be neutral. Because let's say water has no charge, but water is a nucleophile. Why? Because on an oxygen, there are two lone pairs of electrons. So this is going to fulfill the requirements of a nucleophile. So I can say that water is a nucleophile. Same goes with ammonia. Ammonia has a nitrogen. Nitrogen has a one lone pair of electron. If nitrogen has one lone pair of electrons, so I would say that ammonia is also a nucleophile, right? Ammonia is also a nucleophile. So uh, it can be negative, it can be neutral, but it can't be positive. Remember, it can't be positive. Okay. So let's say the general reaction in which I have only reactants and products, that is going to be CH3, CH2, C double bond OH. It's going to react with HC and it's going to give you this product. Same goes with ketone. Same goes with ketone. You can see this is nucleophilic addition reaction. Okay, this is nucleophilic addition reaction. So now we have to do a mechanism. What's going on behind this? What is behind the scene? So the thing is that, of course, I told you carbonyl is a polar compound. Oxygen is highly electronegative. Oxygen would be bearing a partial negative charge and carbon would be bearing a partial positive charge. This it becomes polar. So any nucleophile can attack easily on this compound. So we have a cyanide nucleophile, HCN. Carbon has a lone pair of electron, of course, isn't it? Carbon has a lone pair of electron and else I can remove it, right? It has a negative charge. Okay, so it's going to attack on the partial positive carbon. Carbon cannot make more than 4 bonds. So of course this bond has to break down like that. Oxygen has a lone pair of electron and the cyanide is attached to this carbon atom. Now what would happen? Of course, the lone pair of electron on oxygen atom would attack on this hydrogen and it would become OH. It would become OH. This is called cyanohydrin. Whether you have an aldehyde and whether you have a ketone, this would be the mechanism. Okay, this would be the mechanism. Then, I told you the test for aldehydes and ketone. Let's say you have added Fehling solution and you have added Tollens reagent. Let's say in the case of Tollens reagent, you can't see the silver mirror. What does it mean? If you are thinking that I would be writing that ketone is present but aldehyde is not, so you are wrong. You are completely. What if you would be having an alkene? Of course, alkene cannot give you the positive test with an aldehyde, sorry, with a failing solution or a tolerance reagent. So in that case, what you would expect, what you would think, what you would write. It doesn't mean that if it's not giving you the positive result, so you can write that the ketone is confirmed, but aldehyde is not. No, it's not like that. Okay. So, uh, so before going to do failing solution test or a tolerance reagent test, you need to check the presence of carbonyl compound. Is there a carbonyl group or not? Like, I mean, if there is C double bond O, so yes. First of all, you are supposed to confirm the presence of C double bond O. If there is C double bond O, so yes, then you can go for the Tollens reagent or a Fowling solution. If you can't see any precipitate, if you can't see any silver mirror, so yeah, you can say, you can write that ketone is there, not an aldehyde. But if you haven't checked the presence of C double bond O group, so you can't go for the further test, that is Tollens reagent or a Fowling solution. This is the necessary test before that. So this is called Brady's reagent, 2,4-DNPH. This is called Brady's reagent. What is this? Basically, after adding 2,4-DNPH into the sample, which contains or not contain any carbonyl compound. So if you can see orange precipitate, if you can see orange precipitate, so yes, you can say that carbonyl compound is confirmed, like the compound which has C double bond O, that is confirmed. And if you can't see any orange precipitate, so you would say that the C double bond O is not. And if there is no C double bond O, so it's a completely wastage of time that you are going to go for for a Fowling solution or a Tollens reagent. Common sense. This is the structure for 2,4-DNPH, and this is going to be your aldehyde. It may be your ketone, but what I need to have this oxygen. Of course, this oxygen is present in both aldehyde or a ketone, both, right? So what it would do, H2 and O, they are going to react with each other. The water will be removed and they are going to combine with each other. So I can say that this is condensation because water is removed. Okay. So then we have carboxylic acid. Carboxylic acid is a weak acid. Okay. Carboxylic acid is a weak acid. It partially ionizes. It has a lower value of Ka. I mean dissociation constant for acid, right? It has a lower value of Ka. Ka decides the strength of acid, right? Ka is directly proportional to the strength of acid. So it has a lower Ka. And in the same way, the suffix for carboxylic acid is oic acid. I have just written few family members of carboxylic acid. It may have straight chain, it may have branched, it may have cyclic structure. You will see a lot of things. Hopefully, you have seen uh, in the past paper. Physical properties, they are liquids, yeah, sour taste, soluble in water, higher boiling temperature. In comparison with all, because carboxylic acid, let's say if I'm going to do a comparison between ethanol and ethanoic acid. So ethanol has one oxygen, it can make only one hydrogen bond. But on the other hand, carboxylic acid can make two hydrogen bonds because it has two oxygen atoms, right? So the number of hydrogen bond would be directly proportional to the boiling point. So carboxylic acid would have higher boiling point, simple, common, okay? In the absence of solvent, the two molecules will form hydrogen bond to form dimer. This is very important. This is very important how the dimer is formed, how the two carboxylic acids are going to react with each other in the absence of solvent. If there is a solvent, let's say if we have a water, of course, they will be making hydrogen bond with water. But they're saying in the absence of solvent. So the dimer would be formed. The two part, di means two, mer mean part. So just like that. Okay. But if you have water, it would be making hydrogen bond with water just like that. It's hydrogen bonding. Okay. Again, the same criteria. You have to see, like let's say if I have heptanoic acid, it has 7 carbon atoms as compared to methanoic acid, it has 1 carbon. So heptanoic acid has a longer chain. And of course, the chain of carbon is a nonpolar. If the nonpolar part increases, so means the compound is having the lower solubility in water. In the same way as I told you with aldehyde or ketone, okay? How can we prepare? How can we prepare carboxylic? Of course, first of all, I have to take primary alcohol. After doing oxidation, it would be converting into an aldehyde. If you are doing partial oxidation like heat and distilled, you have to see, you have to focus on the condition what the examiner has written. It's So be careful about the reagent and condition. If there is written heat and distilled, so you are supposed to form aldehyde. If they are saying heat under reflux, so you can form carboxylic acid. So there are two ways to go to carboxylic acid: heat under reflux and heat and distill. Heat and distill would give you carboxylic acid in two steps. First of all, in step one, it can give you aldehyde, and then in step two, it would give you carboxylic acid. And if you are having heat under reflux, it's a single step reaction. So the primary alcohol would convert into the carboxylic acid. Okay, so it's very easy. It's very easy. Then we can do hydrolysis of nitrile, that is going to be C triple bond N. Or in this way, we can also prepare carboxylic acid. Acidic hydrolysis of nitrile can give you carboxylic acid, and this would be inorganic product. Okay, acid is used as a catalyst, by the way. You can also do alkaline hydrolysis, but you won't be getting carboxylic acid. You would be getting the salt of carboxylic acid. You know why? Because you have used alkali. So first of all, carboxylic acid would be formed, and afterwards it would be reacting with sodium hydroxide, and it would be giving you salt of carboxylic acid. Okay. Then, of course, it's a weak acid. It can be reduced to primary alcohol or aldehyde. It can be neutralized with any of the base, an alkali. It can form ester. It can give you acyl chloride. Like, let's say if I'm going to reduce carboxylic acid, so what I would be getting, reducing agent, I'm using LiLH4, the same thing as we have used before. So I would be getting primary alcohol, right? From carboxylic acid, I can get only primary alcohol, not the secondary alcohol. Remember that, these things are very important, so you can simply what's the product, what's the reaction, what's the reagent and condition, and that's it. Neutralization, yeah, acids can be neutralized. Same goes for carboxylic acid as well. Of course, it would be reacting with sodium hydroxide and it would be giving you the salt and water, the same thing. Let's say if I'm going to do halogenation to form acyl chloride. Acyl chloride is a derivative of carboxylic acid. So we can use PCl3, we can use PCl5 as a source of chlorine. Of course, if I have to form acyl chloride from carboxylic acid, so what I need? Cl, chlorine. So where the chlorine come from? Of course, you have two ways to go. Number one is PCl3, another one is PCl5. If you have PCl5, it's a vigorous reaction. No external heat is required because it's already reactive. In the case of PCl5, you are not supposed to write any external heat on an atom, right? So it would be giving you acyl chloride. It's just like that, HCl and POCl3. So you can see misty fumes. Due to the presence of HCl, you can see the misty fumes. And if you are going to react with PCl3, so CH3C again the same product, acyl chloride, H3PO4, and also HCl. Uh, like also we have learned this esterification in the very basic classes. I'm talking about IGCSEs when we used to do that carboxylic acid can react with an alcohol to form an ester. The same thing is there. The same thing, 100%. This is carboxylic acid. This is alcohol. They are reacting with each other. They are giving you ester. They are giving you water. In the same way, I have this one, the same thing. Okay. The very interesting fact in this reaction is that 90% students think that, of course, carboxylic acid is an acid, so they just think that it would give its proton, like hydrogen. But this is not so in this reaction. This is very important fact. Carboxylic acid would give its OH rather than H. We know that this is an acid, but this is not an acid-base reaction, by the way. This is something else. It's not an acid base. Yeah, if it would be an acid base reaction, like in the case of neutralization, when it would be reacting with NaOH, then in that case it can give its H positive ion, but in esterification it's not. Okay, so this is an ester. Or then you can see a lot of things we have. I would be uploading these notes on the link on the comment section in my video. Okay, you can download from there. And acyl chloride, like as I told you, it's a derivative of carboxylic acid. Like you can just replace this OH with a chlorine. Okay, I told you the two ways. So it is going to convert from propanoic acid to propanoyl chloride, ethanoic acid to ethanoyl chloride, butanoic acid to butanoyl chloride. The same thing. But remember, let me tell you one thing. Acyl chlorides are very reactive as compared to carboxylic acid because they have very stronger partial positive center. I'm talking about carbon, right? So as compared to carboxylic acid. So when you are uh, let's say in simple reactions, when you have a carboxylic acid, so there might be need of any external heat, there might be need of any external catalyst or some sort of other conditions, but for sure, if you are going to have acyl chloride, so no need to use external heat, no need to use any external reagent condition because acyl chloride is already reactive. I want to say that, okay? So let's say acyl chloride is reacting with water. It's a vigorous reaction. Despite this is cold water, it would be giving you carboxylic acid and HCl. Again, the same observation, of course, misty white fumes or reaction of acyl chloride with alcohol. Of course, if the carboxylic acid is reacting with alcohol to give you ester, so they would be having the same, but no catalyst is needed. Remember, when we were doing esterification, let me show you that when we were doing so small amount of acid is used as a catalyst. See the difference, that is concentrated sulfuric acid. But in this, no need to use catalyst. They are already reactive. That's the major difference. By the way, the product is same. Like organic product is same. In that, there was water molecule. This is HCl. Okay. Acyl chloride with ammonia, concentrated ammonia, it can give you amide. What is amide? CH3, C double bond O NH2. This is amide. So amide can also be prepared from acyl chloride by the reaction with concentrated ammonia. Remember, okay, and that would be the full equation. You must know this full equation. It would work in most of the questions. Okay. Let's say I don't have ammonia, but I have amine. I have amine, which is a stronger base than ammonia, by the way. It would also be reacting with this acyl chloride and it would be giving you amide. Same product amide, the same product amide. But if you have tertiary, so there is no reaction. So there is no reaction. If you have secondary, yeah, that would be the product. If you have primary, yeah, that would be the product. This is very important. This is very important. I would be uploading the notes as well. Remember, okay. Or ester is very easy. I told you. Yeah, this is also like as I told you, we can hydrolyze nitrile in the same way I can hydrolyze an ester. We have two types of hydrolysis, acidic or a basic. Acidic hydrolysis, acid is used as a catalyst. Basic hydrolysis, we use the base, alkali, I mean to say. So how we formed an ester? Of course, by the reaction of carboxylic acid and alcohol, isn't it? So when I would be hydrolyzing it, basically, I can say this is a reversible reaction. If you know, like esterification is a reversible reaction. We can go from the reactant to product and we can go from the product to the reactant side. So If you're going to react, you would be forming an ester, and if you're going to hydrolyze it, you would be getting the same reactants. Again, simple. What's the difference between acidic and basic? Only this one. Rest of the things are same. The difference is in these two. This is carboxylic acid. This is the salt. And that's it. Okay, and that's it.